This is a video solution for tutorial 3A on graphing techniques, question 5. Question 5 starts off by telling us that the curve C has this equation, where k is a constant, and we're asked to find the range of values of k for which the curve C cuts the x-axis at two distinct points. So we wanted to cut the x-axis at two distinct points. What does that actually mean? Well, where it cuts the x-axis, that's an x-intercept. So we want two distinct x-intercepts. But how do I find an x-intercept? Well, I set y equals to 0, right? So in other words, if I set y equals to 0, I'd want this equation to have two solutions. Or in other words, I want this equation, 0 is equal to x plus k plus k plus 2 over x minus k to have two real roots. So I'm going to try and find the range of values for k for which this has two real roots. I can't do that when there's this x on the bottom line, so I'm going to multiply up. So I get 0 is equal to x plus k, x minus k, plus k plus 2. And so 0 is equal to x squared minus k squared plus k plus 2. Okay, and I want this to have two real roots. So two real roots means what? It means that I want b squared take 4ac to be bigger than 0. So what's b squared take 4ac? Well, b in this case is 0, so because there's no x term. So 0 squared take 4 negative k squared plus k plus 2. And I want this number to be bigger than 0. So let's just factorize that in. A is 1 in this case, as you can see. So factorizing that, I get, or expanding, I get 4k squared minus 4k plus 8 has to be bigger than 0. And I can factorize that as 4k, minus 8, k minus 2, k plus 1 has to be bigger than 0. So I'm going to use my number line method. I know that this has roots at minus 1 and 2, and this is positive. The k squared term is positive, so it's a smiley face parabola. So I get something that looks like that. And I want where it is bigger than 0, so I want this region and this region, because that's where my curve is above the x-axis. So my final answer should be that x is less than k is less than negative 1, or that k is bigger than 2. The second part is where it gets, or starts to get rather, a little bit tricky. It tells us that k equals to 2, and that's quite nice because it means I'm dealing with this equation, y equals to x plus 2 plus k plus 2, so 4 over x minus 2. So this is now the equation that I have. And I want to prove algebraically that y cannot lie between 0 and 8. So, okay, what does that mean? That kind of means, and I'm going to just translate this a little bit for you guys, cannot lie between 0 and 8. Well, what would I say, if instead of I asked a slightly different question, I said, find the range of values of y for which y equals to x plus 2 plus 4 over x minus 2 has no real roots. What would you do? How would you go about doing this? Well, we actually know how to do this, right? We'd treat y as some sort of constant, like we treated k beforehand. It's not, but we'd pretend it were. And we'd form up our quadratic in x and find the range of values for which it had no real roots, right? So that's exactly what I'm going to do. I'm going to pretend y is some constant, and this is x plus 2 plus 4 over x minus 2. What is the quadratic in x? So first thing I'm going to do, multiply through by x minus 2. Okay. And so that cancels out rather nicely on the right hand side, so I get xy minus 2y is equal to x squared. So 0 is equal to x squared minus yx plus 2y. And I want this to have no real roots. So therefore I want, for no real roots, I want b squared take 4ac to be strictly less than 0. So what's b squared in this case? That's y, negative y. So negative y squared, take 4, a is 1, c is 2y. I want this to be strictly less than 0. In other words, I want y squared minus 8y to be less than 0. But I think you guys can see y squared minus 8y, that's just going to be y minus 8. So same thing as before, we use our number line method. This is a happy parabola, and it's going to cut at 0 and 8. And I want my answer to be less than 0, so that happens in this region in here. So therefore, no real roots when 0 is less than y is less than 8. Therefore, y cannot lie between 0 and 8. And we've successfully answered the question in an algebraic manner. Sketch C, stating any asymptotes, stationary points, and axial intercepts. So again, we're still taking k to be 2, right? So this means my equation is still y equals to x plus 2 plus 4 over x minus 2. So to do the easy stuff first, put on the x and y. Now, what do I need to know about this? Well, actually, I've got a lot of information already. What are the asymptotes? I can read these off. This is a rational function, so there should be an asymptote where x is equal to 2. So that's the first thing I'm going to draw, x equals to 2. What about an oblique asymptote? Well, as x gets very, very large, this 4 over x minus 2 doesn't matter. I start having just y equals to x plus 2. So that's going to look something, and I apologize here in advance, it will look something like this. And this is the oblique asymptote, y equals to x plus 2. Okay. What about turning points? So, or axial intercepts, rather. So when y equals to 0, I would get 0 equals to x plus 2 plus 4 over x minus 2. Multiply through, so 0 is equal to x squared minus 4 plus 4. That means that x equals to 0. So when y equals to 0, x equals to 0, so 0, 0 is my x-intercept. And of course, that's also going to be my y-intercept, and in this case, it'll be my only intercept. What about turning points? So again, I'm just going to erase this because I don't have the space here, sorry. What about turning points? Well, what is dy by dx? dy by dx, differentiating this form's quite nice. I get 1 minus 4 over x minus 2 squared. So if that's equal to 0, right, for maxima and minima, what does that mean? Means that 1 is equal to 4 over x minus 2 whole thing squared. Means that x minus 2 is equal to plus or minus square root 4. It means that either x equals to 0 or x equals to 2 plus 2, 4. So I have two turning points, one at 0, 0, which I've already found, and checking on the GC would tell me that it's a maxima, or another one at this point here, which turns out to be 4, 8. How did I get 8? Substitute 4 back in here. 4 plus 2 is 6, plus 4 over 4 minus 2. I'd get 8. And this one turns out to be a minima. So again, I'm just going to erase this because I shouldn't have all of this working on my graph. You guys should be doing it on a plain sheet of foolscap somewhere else. And now I've got enough information to draw my graph. So it looks something like this. That's one turning point. And again, remember, I'm approaching the curve asymptotically. That means I'm always getting closer, never twisting and going further away. Same thing here. Approaching the curve asymptotically, always getting closer. And I'll take a bit of space up here, and I get something that looks like that. So this would be the shape of my graph. This would be what my graph looks like, roughly speaking. And I should, I've labeled my asymptotes, that's good. I have labeled my, intersection points and turning points, that's good. I just need to write the equation of the graph here somewhere. And that is it for me. That's it. So the last thing, the two asymptotes of C intersect at the point P. Show that P lies on the line y equals to mx plus 4 minus 2m for all real values of m. Hence state the range of values of m for which the curve does not, for which the line does not cut the curve. Okay, so the first part, show that P lies on this line for all real values of m. So what would the right hand side be? So, sorry, if you look at this point here, this is when x, sorry, go down a bit. This is when x equals to 2, y equals to x plus 2, so this point here must be the point 2, 4. So I want to prove, and this is my point P, so I want to prove that 2, 4 always lies on this line here. How do I do that? Well, I substitute in when x equals to 4, equals to 2, y equals to m times 2 plus 4 minus 2m. So substituting x equals to 2, so I get 2m plus 4 minus 2m, that's equal to 4. So therefore 2, 4 lies on the curve, lies on the line. So now I know that this line passes through the intersection point of the two asymptotes. Hence state the range of values of m for which it does not cut the curve. So if I go up here and I look for lines that do not cut this curve. Now obviously if I drew a line like this, straight lines by the way, was in the form y equals to mx plus c, so that's a straight line. So if I drew a line like this, that's meant to be straight, obviously it doesn't cut the curve, right? Similarly, something like that, passing through that point, also wouldn't cut the curve. So what would cut the curve then? Well, something that looked like this, right? That would pass through these points here. Or like this. These lines would cut the curve in a couple of places, so I don't want them. So what am I driving at? What I'm asking is, if I drew a line through here, what is the greatest and least gradient m that it could have? Because that's what I've got control of, the gradient m. Well, I can go as negative as I like, because going negative, as we saw, I can have something super, super negative, like, you know, minus 100 maybe. If m is equal to negative 100, that's fine. If m is equal to a half, that's also fine. It's just if m crosses this line, the asymptote, right? As long as if it's still on the asymptote, that's fine. It's just if it gets more steep, that's where we cause problems. And this asymptote has a gradient of 1. So my final answer should be, I want values of m where m is less than or equal to 1.